So good afternoon, everyone. I'm excited to be here and to have the opportunity to present today my presentation, which I'm going to cover at the beginning, who is Rio Tinto and what we do. But I'm also going to dig into soft skills. Okay, so it's not my skill of expertise, but I'm going to try to explain to you the soft skills and what I'm looking for in soft skills for new graduates and new students. And by the end, I hope you know how you can develop those soft skills to help you during your academic journey. So my name is Simon Gravel, like I was introduced. I'm a R&D program manager for reduction cell design improvement at Rio Tinto. I bring over about a decade of experience in the industry, mostly aluminum industry and bauxite and alumina. I worked across various fields during my career, and I eventually led the startup of the new bauxite and residue filtration plant at the Vaudreuil refinery. Later, I joined the ARDC, the Research and Development Center in Arvida, as a research scientist for the bauxite and alumina R&D group. I hold a master's degree in chemical engineering and process engineering from Université du Québec à Chicoutimi, and a bachelor's degree in chemical engineering from Université Laval. I'm supposed to switch slide, I'm sorry. Here we go. This is me. I introduced myself. So let's move on. So before diving into soft skills, I'm going to give you a quick overview of Rio Tinto. We're a global mining and metal company with operation across 6 continents. Our mission is to find better ways to provide the material the world needs, but sustainably and responsibly. Really important. The material we produce are essential for everyday life and the global energy transitions. For example, we have iron ore that produce steel used for infrastructure and construction. We also have copper for renewable technologies like wind turbines and electric vehicles. We have aluminum for lightweight transportation and packaging. We also produce lithium for batteries that powers electric vehicles and storage systems. And we are also investing in new technology like I'm pretty sure you all heard of, which is ELYSIS, which enables zero carbon aluminum smelting. So our goal is to help both our operations and our customers to reduce their carbon footprint. This slide here is showing the wide range of applications for the material we produce, from smartphones to solar panels, from airplanes to packaging. These resources are part of your daily life, whether you know it or not. That's why sustainability and innovation are at the heart of what we do. Rio Tinto operates around the world with a strong presence in Canada. This map highlights our mines, smelters, refineries, and operation centers. And our global footprints allows us to collaborate across regions and bring diverse perspective to our work. But looking more closely at the eastern part of Canada, you see that we have several key operations here. We have our corporate and business units here in Montreal, across the road basically. And we have multiple smelters dedicated for primary aluminum production located in the Saguenay-Lac-Saint-Jean region. We also operate a bauxite refinery, the Vaudreuil refinery that I mentioned earlier, that produces smelter-grade alumina for essentials for the smelters we have. We also have the Arvida Research and Development Center, where I work, and it's one of the largest industrial R&D center of its kind in Canada. We support the entire aluminum value chain through innovations and applied research, and we provide technical assistance for the production sites that we have in the region. Here I'm showing a map of aluminum production around the world, not only Rio Tinto, but the whole production of aluminum. You can see that in 2024, North America produced 4.1 million tons of primary aluminum, in which 3.3 million tons was produced in Canada. And Rio Tinto is a major contributor of that total. We have a strong relationship, as you know, with the United States. We have a strong trade relationships between the two countries. And because the US is consuming about 10 million tons of aluminum per year, coming mainly from primary aluminum and from recycling. This slide shows a comparison of the carbon footprint of aluminum production across different regions in the world. As you can see, Canada on top here stands out with the lowest carbon emissions per ton of aluminum produced. This is largely thanks to our hydroelectric power, which is clean and renewable, really important. In contrast, you can see that China and the Middle East have more impact because they are more relying on fossil fuels for the aluminum production. At Rio Tinto, we're proud to produce aluminum in Canada with one of the smallest environmental footprints globally. This gives us a competitive advantage, especially as customers and governments are seeking for a low carbon material, low carbon aluminum. So before we move on to the main topic of this presentation, I'd like to share a short video that brings our values to life. At Rio Tinto, we talk a lot about care, courage, and curiosity. But what do these values actually look like in action? This video features real voices from across our global operations, people who live these values on a daily basis. You'll also get a glimpse on some of our incredible sites and the diversity of our teams. But what's powerful about this video is that it doesn't just show what we do, it shows how we do it. And that's the connection with today's topic. These values are deeply linked with the soft skills that we're going to talk about next. So let's go ahead and watch this video.
From safety to continuous improvement, our culture is all about finding better ways for everyone, everywhere,
every day.
Our values are at the core of our culture. Care, courage, and curiosity are more than words.
They define who we are and how we show up every day in every site, location, and office around the world.
Lasting culture starts with the simplest everyday behaviours and actions.
I take care of the safety of myself and others.
I show I care by creating an environment of trust.
I care about the impact my team and Rio Tinto has on others, communities, and the environment.
I have the courage to show vulnerability by seeking out and offering feedback to continuously improve performance.
I have the courage to speak up and challenge when we can do better.
I have the courage to take ownership of my actions and outcomes to contribute to our collective success.
I use my curiosity to learn, grow, and remain relevant in what I do.
I spark my curiosity by looking for opportunities
to continuously improve with everyday innovation.
I expand my curiosity by exploring and being open to different perspectives from colleagues and the wider world.
Together, we are building an environment of trust,
where we all feel safe, respected, and empowered.
It's how we get it done, the Rio Tinto way.
We are Rio Tinto.
This is our story.
All right. So now that we've seen this video, you've seen our values in action. But let's take a closer look on how we actually live these values every day. This framework here I presented is more than a poster. It's something that we use actively at Rio Tinto, even for performance reviews. It helps us reflect on how we show up at work, how we interact with others, and how we contribute to our teams and our communities. So for each values presented here, of care, courage, and curiosity, we've identified specific behaviors to guide our actions. For each, we have care. To start, care is about safety, trust, and impact. It's about looking out for one another, creating a respectful environment, and caring about the consequences of our work. Courage means being open to feedback, speaking up when something is wrong or something has to be improved, and taking responsibilities for our actions. And curiosity is about staying open-minded, continuously learning and seeking out better ways to do things. But what's powerful here is that these behaviors are directly connected to what we call soft skills. Things like communication, leadership, adaptability, emotional intelligence, and so on. So this framework is a bridge between our company culture and your personal development. And that's exactly what we'll explore in the next few slides of this presentation. And I can say that it's just not Rio Tinto that values soft skills. You can see here a quote from Jim Link, a former Chief Human Resource Officer at Randstad North America. And if you read this quote, you can see that it highlights what many employers are seeing today. We're seeing a gap in soft skills among college graduates. But the good news is that you can start to develop those soft skills now. You can practice them in many ways during your academic journey, and I'm going to give you some good examples later in this presentation. Soft skills will complement your journey and your technical knowledge and help you integrate work more easily. This slide presents a key insight from a survey that was conducted by C-Engage and Morning Consult. And what it shows is a clear disconnect. While student often feels prepared for the workforce, many employers report that new graduates are lacking essential soft skills. Things like communication, critical thinking, listening, and problem solving. So visually, this image shows that employers are saying that it is difficult to find candidates that has the right soft skills for their company. So I'm not asking you to replace your technical skill. I'm asking to maybe complement them. It's the human skills that will make a difference in the workplace environment. This other slide here is building on the previous one. So you can see how the job market is evolving. Because this one is not just good for new graduates, it's good for everyone, basically. Because automation and artificial intelligence continues to transform our industries. The demand for purely technical and repetitive skills is decreasing. What's increasing, what is rising, is the importance of the skills that machines can't replicate. Things that we call uniquely human skills. These include things like empathy, creativity, adaptability, and emotional intelligence. They're the skills that allows you to navigate complexity, work with diverse teams, and solve problems in a way that goes beyond algorithms. So the image here illustrates this shift. While technical skills remain important, as you can see, it's the human side of work that's becoming the differentiator. This is why soft skills are no longer optional. They're essential, and the earlier you start developing them, the more prepared you'll be for work. So here I've gathered some of the most important soft skills that I personally look like when building a team, and something I will try to learn during interviews as well. This includes teamwork and communication, because no one works in isolation, especially in complex industrial environment. Attention to details and problem solving. They're essential for safety, for quality, and innovation. I also have adaptability and stress management, because things don't always go as planned, and how you react matters. And finally, I have initiative, responsibility, and a growth mindset, which shows that you're proactive, accountable, and always looking for better ways to do things. So now that we've seen a couple of soft skills that are important, I'm going to talk about how we can actually start building them right now during your studies. I have a few examples. For clear communication, you can practice this through class presentations, writing lab reports, presenting posters, presenting at conference like here in a conference of metallurgists, or even explaining technical concepts to non-experts. For teamwork, you have group projects and labs that are great opportunities for sure to learn how to collaborate, share responsibilities, and resolve conflicts. You have time management. You can practice this by balancing multiple courses, assignments, and deadlines. It teaches you how to prioritize and stay organized. You have critical thinking, whether it's solving a complex problem in class or analyzing studies. This skill helps you approach challenge with logic and creativity. Adaptability. Learn to work with new tools. Adjust to different professors' expectations and adapt to change. Initiatives. Get involved in student clubs, lead a project, or volunteer for something outside of your comfort zone, like I'm just doing right now. It shows you're proactive and engaged. And ethics. Respecting academic integrity, being honest in your work, and treating others with respect are all part of building a strong professional foundation. And I'm pretty sure all of this is something you're already doing. But being intentional about it, what's make them more important and will help you to grow. But let me be clear, technical skills are really important. It's what qualifies you for the job. It's what will make your resume be noticed in the first place, and what will allows you to apply for different technical positions. But here are the key points. They're not always what makes your hiring successful. Once you're in the interview, and especially once you're on your job, what really sets you apart is the soft skills. Your ability to communicate, to collaborate, to adapt, etc. And this bar graph shows a recent study from about 1,000 business leaders involved in the hiring decisions, and it shows that recent college graduate hires haven't been successful for various reasons. But you can see that technical skills is here, but all the rest is around soft skills. So remember, people or industry are not only hiring a diploma, they're hiring a person. We also have extra challenges in the mining industry. It comes with a unique set of challenges for sure. We often operate in remote locations with long shifts and under strict safety protocols. And the work environment is multicultural, and the conditions can be both physically and emotionally demanding. And all the soft skills that I presented are really important and essential, I could say, for the business. I've talked about adaptability, communication, stress management, resilience, teamwork, empathy, leadership. These are just not nice soft skills to have. It's important that you have them so you can stay safe and support others in a challenging but rewarding industry like ours. So a few final tips to help you guide you to develop your soft skills during your journey. I would recommend you to basically join a student club or a competition and build your teamwork and leadership. Take internship or summer jobs because it will gain you real work experience. Practice receiving and giving feedback. It's really important as well because it's a powerful way to grow. Learn and explore new digital tools to stay relevant, because we all know that you are the one who will bring new tools, new things to the business that will help us grow. And don't hesitate to ask for mentorship or career advice. So remember, soft skills are not just complementary, they're essential. They help you build strong relationships, adapt to change, and grow both personally and professionally. Before I wrap things up, I want to highlight Rio Tinto's graduate program, which is designed to help new hires not just start a job, but launch a meaningful career. It's a two-phase journey. The first phase is about onboarding and integration. You'll learn about our operation, our safety culture, our behaviors, and our values for everyday work. You'll also build your professional network, develop resilience, and gain deep understanding of our value chain. This phase is about giving you the tools and confidence to navigate new environment and start contributing from day one. The second phase of the program is more focused on professional development. You'll take on real responsibilities, work on impactful projects, and receive mentorships from experienced leaders who are invested in your growth. You may have the chance to explore different areas of the business around the world, connect with peers, and shape your own path within the company. But what makes this program so special is that it's not just learning, it's about becoming. Becoming a confident professional, a trusted teammate, and someone we can rely on and make a difference in the industry. At Rio Tinto, we are always looking for curious, motivated, and creative people who wants to make a difference. You can explore opportunities on our career website. I've put here a QR code, and we have a poster outside also with the QR code that you can scan on that will direct you to our career website. And before we close, I want to mention that I'm actually hiring right now in my team. I have an open position for an R&D scientist. So if you find this presentation, if you learn something from this presentation, or if something interests you, don't hesitate to go directly on the career website and submit your application for an R&D scientist position, and we'll be in touch. So thank you very much for your time and attention today. I hope this gave you a better understanding of the role soft skills play for our industry and how you can start building them right now. Thank you. I'm not done, I know. Yeah, for sure. I focused on the aluminum part because it's the one that I know, but yeah. If I was a student, what would I ask myself? Go ahead. You, yeah. What is the soft skill that served me the most is communication and be open-minded. What helped me a lot during my early career is the fact that I was always going to go search the information with the people that knows it. Like I was close to the operators, I was close to the technical department. I was working in the technical department, but the conseiller expert, which we call experts. And talking and communicate is something that helped me a lot because I learned a lot from them, and you can learn a lot from operators. You can learn a lot from the people that is working hands-on in the field, and that's what served me the most in the earliest part of my career. What now can maybe help me most is my leadership. I developed leaderships across different positions, but it's what makes me now more confident and more open to take decisions, to take the right decisions, and to help my team grow, basically. Yep. Oh, soft skills wise. I'm gonna start for the technical side. I have a position open for material and material engineer, scientist, I could say. But let's dig up on the soft skills part. We are working with various people in my team. We're working with the operation. We're working with the different sites, and the fact that we are working with so many people can be sometimes frustrating, but can be sometimes so rewarding. So I mentioned communication is really important. We have a whole team and you're not working alone. You're working with a lot of people, a lot of experts, a lot of operators. So communication is really important. Soft skills wise, I think it it's a fit. Like, you know that you have to collaborate. You know that you have to think and develop your skills to bring a new project to life, because we're building new projects that are implemented in the plant, and not in the refineries, but in the smelters. And it's what I'm looking for in a person, soft skills wise. So collaboration, adaptability, and communication.
Okay.
Thank you.
Yeah, it's okay. So my question is that, as a leader, suppose one of your team member had done something wrong. Okay, could you give a specific, or actually a tricky way to tell, if you did not develop your soft skill, how you were going to treat the member, and if you had developed already, how you are going to treat him?
If I got your question straight, I think there's no errors there's no damage in doing errors. What is important is how you're open to evolve, how you're open to learn the skills to make sure you don't repeat that error. So my role and my position as a leader is to help you grow. And we have a lot of resources. Rio Tinto is a big company, is wide, and we have a lot of resources to help develop technical skills, but soft skills as well. So I personally followed a lot of formations for soft skills development. Leadership programs is one example for a leadership position. So there is no error, because I'm going to give you the right tools to develop yourself. But what I'm asking and what I presented today is that if you develop them early in your career, in your academic path, it's going to make a difference in the interview, and it's going to make a difference day one. Because if I have the confidence that you have all the soft skills necessary to take on big projects, to explore different units, operation units, I'm going to give you this opportunity, this opportunity. Because if you have the soft skills, all the units are open for you.
Do you mind if I rephrase your question? Because I liked your question. Let's pretend I am your junior engineer, and you asked me to do something, and I came back and I did something that wasn't what you asked. Talk about talk about a manager who's not well-formed in communication skills, how they would respond to that, versus someone developed as you are in these skills, and how those two scenarios would play out differently.
I'm not sure I get the question. I'm sorry.
I'm a junior engineer, and I'll come to you. You get the next question. So I'm like, oh, boss, I just realized now I didn't do what you asked me to do. I did something else. So I made an error. So person A is not a well-developed person. And then person B is. How does person A respond to that as a manager for that engineering mistake? And how does the well-developed person respond to that?
Oh. It's a good question.
That's a good question, not mine.
It's a really good question. So I did not answer your question at all. You got me right there. All right. How person A versus person B will
respond to, like, I screwed up.
Actually, I'm losing my word now. My words. I don't know. I think I'm going to get that question, think a bit about it, and get back to you. Okay?
A few days.
All right. Or maybe I'm going to think about it, and the panel later on, I can respond.
We'll
I'm sorry.
Time after to discuss. It's a great question. No,
it's a great one.
And then you had a question.
Sorry. Yeah.
Sorry, before you ask your question, can I say that it's always great to see an expert say, like, I don't know. All of you in PhD defenses, I always ask a question that they shouldn't know, and if they make up an answer, I destroy them. It's okay to say you don't know. Respect. Just saying.
But it's hard. It's hard. Go ahead.
No one knows everything. People feel like they have to know. So did you get the microphone? You did. Good.
Yeah. Thank you for your presentation. My question is quite simple. because communication skills is very important, as you mentioned, but what to do if a person is introvert?
Oh, sorry, I didn't get the last part.
What advice can you give to an introvert person?
Oh, what advice can I give? I make, for me, in my mind, introversion and communication is different. Like, you can be an introvert and have excellent communication skills. So what I would recommend for an introvert person is to maybe prepared for nice communication, but maybe know your limits and know where you excel in communication, because there's different type of communication. You can communicate by writing, and you can communicate by presenting. And if you present, what I would recommend is to be well prepared, and well prepared is the key, basically. So prepare yourself. You know you're an introvert person. Prepare yourself. It's going to be hard. It's going to be a bit stressful, but at the end, it's going to be rewarding because you have a message to communicate, and how you communicate it is really important. So be prepared to what message you have to say and share it. So communication and introversion is different. You can be introvert and have excellent communication skills. Go ahead. Do we have time?
Yes.
All right.
For you, of course.
Oh.
Thanks for your presentation.
Thank you.
Each company includes some different parts. For example, R&D, quality, insurance, and also supplier parts for supplier raw material and other parts. And for example, I work in the quality, for example, in R&D, but I have an idea for supplier department or other department of the this company. How can what is the Rio Tinto approach to receive the suggestion for different parts? To, as I said, for example, I work in the quality control, but my responsibilities is defined, and my boss expects me to have innovation in quality control department. But for example, I have a good idea for supplier department to have a benefit financially and decrease cost for company. How can send my recommendation for the manager of the company to implement, because my boss may.
So I'm going to interrupt. Sorry, if you summarize the question, because we don't have all the day. Sorry.
No,
Is the question like, how do you work outside of your department to send messages about improvement?
I know exactly how to respond to that. First,
I wanna
Emily, sorry to cut you off. Sorry to cut you off. I'm going to cut you off because we have two other presenters and we have to leave the room. So thank you.
I'm going to respond briefly. But first, you're showing curiosity because you're thinking of things outside of your department, outside of your position, and that's really encouraging Rio Tinto. Second, my role as a manager is to get your idea or to receive your idea and open you the doors to share this idea. So I'm going to present you with courage. You have the courage to talk with other departments. Go ahead. I'm going to open you the doors, show you the right people. If I don't know them, I'm going to search for them for you, and I'm going to get you in contact with those persons. The other thing that I can mention is that in Rio Tinto we have, how do we call it? Maybe I'm losing my words here, but it's like innovation program. Each year we receive ideas that are from people that are outside of their field. To maybe Isabelle, you can help me on that one. The pitch project. There you go, the pitch project. So we encourage people to submit their pitch. What idea do you think can be of great service for the company? You submit your pitch, we have a revision panel, and if your idea is selected, you can have direct financement for your project. You can be in contact with a lot of experts to develop your projects. So we encourage those behaviors. So it's a really good question, but it's really important in Rio Tinto to share those ideas and not leave them on the table, not be closed on a specific position. All right, thank you very much. Thank you. Thank you. Oh, thank you.
Thank you so much. The next presenter is from Trilion Pacific. It's Charles-Olivier Amyot. He's the Regional Engineering and Account Manager. Thank you very much for coming. The floor is yours.
All right. Okay, I don't know if I'm going to last with this mic or switch mid presentation, so we'll see. I'm super happy to be here with all of you. Cindy was just saying, my name is Charles Amyot. I work for Trilion Quality System. My day-to-day job is to work with cameras to film materials and prototypes. So that's what I'm going to be talking about today. Presentation is going to come up here in a second, but I wanted to go back in time a little bit and give a bit of an overview since I'm immersed in camera technology. I want to talk to you a little about changes in the camera world and how that might impact you in material and science realm. So first I'm going to talk a little about evolution of digital imaging in the last couple of decades, how and what are the applied challenges that you have in metallurgy and material science research, the paths forward that have been developed in the past 10 or 15 years, and how do these integrate to solve those challenges, hopefully for you in your labs. So first off, evolution of digital imaging. I mean, cameras used to look pretty big, pretty large, and quite heavy. We all have one in our phones now, and actually we probably have more than one in our phones. Back in the 70s, large CCDs were what was coming up. Front illuminated design was the key thing here. That meant that we had the light hit up the sensors, and we would build image, but all of the structure holding up the pixels would be underneath those pixels and support the image being collected. In the 90s, we had new technologies come up to reduce and make faster and cheaper sensors. And then in the 2000s, we have the first iterations of backside illuminations. You'll start seeing these, and you possibly already have, and you've just never noticed it. And hopefully in the next couple of weeks, you'll see, oh, I see this now. The acronym of BI or BSI, meaning backside illuminated sensors. Those sensors mean that we've moved all of the pixels. Instead of being the structure on top, it goes underneath. And now all of the sensor can detect light directly at the top of the pixel map. And so you gain a lot more illuminations. These were extremely expensive to make, and as we're developing new different technologies to manufacture silicon chips, we also improve on how we make cameras. We had a massive change in the 2000s with the iPhone 4. That change is actually, to this day, our research world, really, because they've implemented the very first backside illuminated sensors in the iPhone 4. And that's just started the spread of a different change of camera technology, miniaturizing, but also improving sensitivity and quality of data that you can get with cameras. Today, we have new sensors that are being rolled out on every single scientific products. If you go outside and you check all of the different vendors and exhibitor, you can probably identify multiple sensors and detectors, be it in the X-ray microscopy, be it in the microscopes themselves, cameras. Most of the things out there have cameras, have detectors, and guess what? They're being powered more and more by backside illuminated sensors. If you go out and buy equipment today, I would encourage you guys to ask questions about this, ask questions about the sensors, because this will mean a lot cheaper and a lot higher quality data moving forward. Okay, so that's just a little path or down memory lane. Now, what is a front illuminated sensors and what is a backside illuminated sensors? So first, obviously, the front illuminated sensors are extremely simple designs, extremely simple to fabricate, and they're mass produced for a long time. It's two different ways to build the image, either with a global or rolling shutters, meaning we can read a line of pixels and kind of refresh rate really quickly. So these are extremely common, and they've been around for a long time. But global and rolling shutters from illuminated sensors would give you really distorted images. If you have anything moving, anything dynamic, imagine you're trying to take an image on your microscope, and you're just holding that plate down. It needs to be extremely stable, otherwise any blur will create a blurry image. Motion will create a blurry image, and bad quality or bad images data. Now, improving sensors and moving to backside illuminations also mean there's two verticals that we need to play with over time: frame rate and resolutions. And you do the same thing on your day-to-day cell phones. You want to get a camera that has more pixels and that can go slower. You can get high res and slow motion images. This is, again, getting more true and true in the scientific field, and it has a big impact on the type of sensors that you can select in your instruments. We also have two other bases to illuminations that are all pulling in each other's directions. As light sensitivity, you can have a really looking high-res and fast camera, but if the images is extremely poor quality, it's going to be really grainy. We see this now more and more, unfortunately, in videos. If you watch the videos on Netflix or whatever, Crave, or other streaming platforms, you'll see all of those blacks being extremely pixelated, and that's the black noise sensitivity. You get that in every single image sensors. These are artifacts created by compressions when you watch the videos, but you also get it when you take an image of your sample. That can interfere with what you're actually trying to measure, and it can interfere with your algorithms to do image detections if you're trying to detect different types of grains and so on. And then finally, you have bandwidth, because if you're trying to have a really high-resolution sensor that goes really fast, you're trying to send a lot of pixels to your memory, to your computer, at a really fast bandwidth, a really fast rate. So balancing out all of those things is what makes, more often than not, the cost of any of the tools you're going to buy in the scientific world. If you have a high resolution, high speed, great sensitivity, and great bandwidth camera, you have a very pricey equipment. And balancing out which of those fits your needs for what you're trying to do will make a system that is well priced. Okay, so just a couple of things or applied challenges that we have in metallurgy and material testing. I have here a composite tensile test duck bone, and you can just see the shear fractures being built up to about 2% of strains here. That's the core images from our main product line at Trilion called Aramis, a digital image correlation system. I'll talk a little bit more about it in a minute, but some of the challenges that you have and in which new sensor technology really changes the game. Complex natures of your materials, you're trying to do new types of alloys, change the structures of your materials, try to have complex structures, additive manufacturings, different types of curing, different types of temperature change in profiles as you're building up the samples. That can heavily impact the structure of your material, and having globalized informations and just global strain information of the part doesn't really tell you what is really going on into your sample, into your part. Again, accuracy and details and imaging, these usually mean you need to have really fine optics, really high resolutions to get those small defects, and also very low noise, because if this moves a lot from just pixelations of your black noise, then you get bad data. Different example here of a part also that has really localized fracture mechanics, and how we implement the different materials that we're working on into a real-life prototype and a real-life product means we need to be able to qualify exactly how the products will behave, and how is the material that we're designing, possibly trying to design a better material, how does it affect our prototype in a different way. So being able to test and really measure these locally is extremely challenging. Okay, so I mentioned my day-to-day is measuring with cameras. Our core algorithm, and you may have heard of it, maybe some of you have used it in some of the papers. I did see downstairs some modulus calculations and resistance properties of materials, is a digital image correlation algorithm called Aramis. We use two cameras to film any object and any materials in 3D by getting triangulation. So if I can find a defect or a feature on your sample with one camera, I can triangulate it with the second one and see how does that part move in 3D space. Taking image over time, I can see how these parts move. Are they getting stretched, compressed, deformed? Do they buckle? And so on. In this case here, it's just a tensile test. In this case, we're seeing necking. But once again, we're seeing the really small, refined bands here, giving us the ability to measure Luder bands, in the material, and localize necking as well, to really quantify, especially in aluminums and other metals, really strong behaviors and large deformations. The little icon that you see next to the image here is that little speckle pattern, the black and white paint. We usually just apply this on the material, and that gives us contrast so we can track how the part is behaving. And that gives us the identifier over time. Imagine it's kind of like applying thousands of QR codes on a part, and we take our image down and we break it into thousands of small puzzle pieces, and we track how each of these pieces are moving. I'm sure some of you are already thinking about, wait, can I use this in my different measurements? And the answer is obviously yes, you can. There's a lot of open source algorithms that uses this. We also offer our software actually from Zeiss Correlate for free. So you could start doing 2D DIC if you wanted to today. Come and ask us questions. Come up to Oskin's booth, who represents us as well, if you have any questions about that. But moving on into camera technologies and sensitivities, obviously if I'm zooming in so much, large, the question of how many pixels do I have, how many can I fit on my part is extremely critical here. The smaller the pixel size, the smaller defect or artifacts can I track. And then the zones of which I'm going to be tracking each of those pixels gives us a mesh and gives us the ability to track how are they expanding from one another or compressing from one another, and again, getting strain informations very locally into small samples. So again, some of those challenges that we've mentioned here in your world of metallurgy and materials is small deformations, ceramic materials, and so on. And you need to have very low noise and really great light sensitivity to capture that kind of defects. Fine deformation gradients, you need a high spatial resolution, be able to see a crack show up in the sample, localized strain. Brittle and dynamic failures, especially if you're working with stronger and stronger alloys and ceramics, you're going to need really high frame rate to capture the last moment before impact or before failure of your sample. You need thin laminate cross-section instrumentations, for example, 3-4 point bending. That means you need, again, very high spatial resolution if you want to be able to capture through the thickness of your sample what is going on in your structure. So very large, very small, you need high magnification and large camera capabilities, and then we're back onto our triangle of just what pillars do we balance things on based on your unique challenges. One thing that has heavily grown in the last few years, like I said, is the switch from front-side illuminations to backside illumination, moving what we call the Bayer filter, or the pixels that are collecting the light, from being at the top of the, at the top you have the filters that lets light through and separate things down. Then you have the layers and the wires that connect all the pixels together. And underneath you have the detector that will receive the light. So the light needs to go all the way through and all the electron needs to pass through those wires and those coppers, giving us maybe 40 to 50% amount of electrons that can actually reach the sensors and build an image. Moving up to backside illumination sensors instead, we're switching where the wires and coppers are, and you still have the filters at the top to separate colors and such, but by putting that up here, we increase the fill factors at least by a factor of 2 in most designs. That means you can heavily reduce noise because you can expose for a fewer amount of time, and you have pixels that can be smaller and shorter. Now, having really large detectors has been the biggest challenge for backside illuminations for adoption, because making a structure like this is not extremely structurally sane, and so these would buckle. If you were trying to do a really large detector and take a really large full frame camera, you would need a camera chip that would be so big that it would just waffle and wouldn't stay structurally safe. So these changes have now happened, and you can see massive increases in quality. Not only can you see increase in quality images, but you can also see here a backside illuminated sensors that have much smaller pixels, meaning on the same size detector, you can put more pixels and go from 2-3 megapixels in HD resolution to 4K that we're seeing in videos and movies now. That also allows us with sensitivity to reduce the exposure time and capture things that happens faster. Backside illumination sensors, you can see on the right side, makes a darker image become brighter. So the impact of the sensor size means we can shrink the pixel size, still have a really bright image. And so image at night with your phone becomes better and better because you don't need to be steady for that long, and you still have high resolution on a more light sensitive sensor. Okay? And then the second part that has proven to increase a lot development here is resolution changes, allowing us to bind pixels together and combine different sources so we can go much faster. So taking 2 pixels by 2 pixels on our phone can make a binned image that reduces resolutions, but is a lot, again, higher sensitivity, which faster readout, but overall gives you a cleaner image with lower data, with lower noise, data. Going to skip up a little bit here, just a sanity of time. And then in resolution realm and having more pixels on those detectors, that means we can get a much finer resolution map, and you can see the difference here really well between a 6 megapixel and a 24 megapixel sensor. Okay, we do have more and more of these that are coming, like I said, into the realm of accessible research products, tools that you can use in your labs that are embedding these higher resolution, higher sensitivity cameras. This one is one of our newer cameras, 24 megapixel from 12, and before that 5. We were just at EDS this morning visiting a team that bought a sensor about 10 years ago that was using 5 megapixel. And now for a lower price point, without inflation, which is wild, you're buying cameras that are a lot more sensitive. And these can open up new areas of development in what your research can be. Research that might have been kind of closed and wrapped up 10 years ago, today becomes accessible and might be your next research project thanks to these change in camera technologies. Okay, so just showing up that these cameras can offer a lot of variations in resolutions and speeds. You can go and open up new kind of doors in research again by being able to go faster and collect data from things super dynamic like human motions, these titanium blades and prosthesis here being able to be measured at up to 270 frames per second and seeing actual live displacements of an athlete. Okay. I want to make sure that we have time because we have, I think, 15 more minutes for the last presenter. So I think that's about it for me. The last one here, just to show you strain and tension measurements on a load frame tester, which, again, some of you are probably doing since I saw data downstairs on the posters, which is that, well, our capability in those higher resolution cameras can allow us to get automated stress strain curve data locally and not just globally, and we can calculate all of the material properties as they change on different samples. So just improving capabilities of test setups. Okay, that's it for me. I think Sydney probably, I wasn't sure if you were ready for it.
I think we have time for one quick question from the students. Yes.
Yeah, so the question is, front-side illuminated sensors seems to have benefits compared to backside illumination sensors. So initially, it was definitely technical capabilities of manufacturing that limited us from being able to switch from front side to backside by moving the wire and the copper layer underneath instead of being kind of in the middle. That would create integrity. So the first CCDs and other ways to create those crystals required us to build it with the front illuminated types of technologies. It's really the improvements with like miniaturizing our silicon chips for CPUs that have allowed us to transfer this knowledge into chip making for cameras. Okay. All right, thank you so much. And like I said, we have a booth outside with Oskin Scientific. So if you have more questions, don't hesitate to show up and ask more questions about your research.
Thank you for your very excellent technical presentation. I feel like we could put you like in the clean room and you could just do things. And that's like amazing to see such technical skills. Thank you very much.
Thanks.
Thank you so much. Great. And our last speaker is from the Department of Chemical Engineering at Polytechnique here in Montreal. I'd like to welcome Professor Patrice Chartrand.
Thank you, Sydney. Thank you very much to the organizers to invite me to this nice luncheon. I hope you're enjoying your time. I'm from Polytechnique Montreal. I'm in the group, the Center for Research in Computational Thermochemistry, where we are one of the main hubs of the development of the FactSage software. So I would like to present you FactSage very quickly during this luncheon so that you have an idea of a tool that can help you either as part of your current academic research projects or in the future in companies for developing the chemistry, chemical aspects of material science and metallurgy. So what FactSage can do for you? So FactSage is a thermochemical software package. It's using thermodynamics to compute the estimation of phase equilibria and thermodynamic properties for high temperature applications. We're more on the chemical part here of material science and metallurgy. So if you're working on projects involving smelting, pyrometallurgy, it can be molten metal treatment, alloy design, high temperature corrosion, glass slag, refractory materials, their corrosion. But also it's very much used in the development of small modular nuclear reactors now. Material science in general. So it's a tool, it's a series of databases and calculation modules that permit to answer simple questions about phase equilibria. You're going to the lab, you're going to put something in a refractory or in a container, you're going to raise the temperature. Is there something wrong that can happen? So you can use this virtual simulator in order to have some idea of what's going on. So that can help you, but it can also be used for designs of processes and more deep question. So who are developing this software? It's a software that started a long time ago at Polytechnic and also in Germany in the 1980s. So there are several groups. The main development groups are at Polytechnic, our research center. Professor Arthur Pelton and Christopher Bale started the software on mainframes computer at the time in the 1980s. I joined as a student in the middle of the 1990s and as a professor in 2003. And Professor Jean-Philippe Harvey is also with us in our group at Polytechnic in Montreal. So we are doing the theoretical aspects, model, software, and we're also heading an aluminum consortium of 5 companies. I will come back to that later on to show you some results. Our partners in Germany is a spin-off of RWTH in near Haken, Germany. It's called GTT Technologies. Dr. Gunnar Eriksson and Klaus Ack were the main developers of the time, but today Stefan Petersen and Moritz Tubaben. They concentrate on software development, but also on energy conversion. There's a lot of coal combustion and reactors in Germany that are using FactSage for their question. Main collaborators, if you're from McGill, you may know Professor Ino Jung. He's now at Seoul National University. He has a big group there with the Steel Consortium, heavily relying on FactSage for all steelmaking operations. Consortium of around 16 companies there. Philip Spencer from the Spencer Group, it's more on hard materials, silicide, carbides, nitrides. Eugene Jack, Professor Eugene Jack in University of Queensland in Australia, has a smelting consortium for copper, nickel, converting. Rio Tinto is one of them there, and Daniel Lindberg in Aalto University in Finland. Corrosion smelting, but also pulp and paper and biomass conversion. So all these groups are developing things, but what's behind? What are the theories behind FactSage? So be prepared for a couple of slides of theory and a small exam after. No worries there, but basically it's quite simple. For every chemical phases in a system, we want to have a Gibbs energy function. So that function has derivatives which we can relate directly to experimental results. So the Gibbs energy function is what? It's an enthalpy contribution and entropy contribution, and they have to be taken from a theoretical strong background. So there are differences of bond energies, configuration of atoms, defects that can come in, which can affect the Gibbs energy. So from this theoretical function, you can make derivatives. So as you can see, I think my laser, you have derivatives that will relate to calorimetric measurements. So you have labs with DSC, with calorimeters. So for specific points of temperature, pressure, and number of moles or mass of your different reactants, it's possible to obtain an enthalpy, a difference of enthalpy in the lab. And CP will be a derivative of the enthalpy. It can also be measured. And these are also confronted to first principle calculation, which challenges the people in the experimental sector. Then you get another series of derivative of the Gibbs energy will relate to chemical potential. You can have activity related to that, partial pressures. If you have a Knudsen cell measurement to measure partial pressure, electrochemical techniques to measure activity, and at phase equilibria, the chemical potential of the different phase components in the different phases would be equal. So you can relate it to measurements of phase equilibria, which you can do in a lab. And this is all for different temperature, pressure, and compositions. And if they are all related to the same chemical system, they must relate to the same Gibbs energy function. Other derivatives of The Gibbs energy with temperature and pressure will give you thermal expansion, the volume of the system, and these can also be measured independently. So the idea here is if you get a good function with chemical-specific parameters for your Gibbs energy, you can reproduce these experimental values with a proper set of parameters and then store that and use it to compute in other conditions the phase equilibria, but also phase properties. We pay a very special attention to liquid phases in FactSage. We think it's very important. A lot of chemical processes, metallurgical processes at high temperature use the liquid phase as the main reaction phase. So it's very important to have it in smelting, BOF operations, and others. So just if I come back there. But it's also for a different set of reactions. For example, solid gas reaction, solid gas reactors. Sometimes you want to avoid the apparition of a liquid phase, and some reactors are operated very near the appearance of this liquid phase. So having a good model to predict at which temperature it can occur can be quite critical. And in liquid solutions, there's a lot of short-range order that can happen. These are the way the atoms are configuring themselves in order to minimize the Gibbs energy. And that stabilizes usually the liquid phase. So with FactSage, historically, we put a lot of emphasis on these liquid phases and short-range order in liquid phases. So an example here, we use either bond or quadruplet interactions. So when you're mixing A and B's, for example, you create new pairs of AB which have a different energy, and the enthalpy can be either rather small or very negative, like in ferrosilicon. And then you get a V shape here of the enthalpy versus composition between A and B. And the entropy is correlated to it. The configurational entropy will tend to go to 0 at the maximum ordering configuration. And we are one of the only software who's using correctly this type of short-range order. So for pyrometallurgical application, this is quite critical. Then we need a calibration of our thermodynamic models. So the Gibbs energy functions for every phase, this is a thermodynamic model, and we can calibrate it with its own data or with relation with other phases in a complex chemical system. And this is an example of how we do that. We have to collect all the experimental data that are available for a chemical system in terms of thermodynamics, phase equilibria, and then by an optimization technique, we find the values that best suit the experimental points. But there could be big challenges, is which set of point is better, there can be conflicts, and as you can see here, I'm presenting two different set of parameters that are used in the FactSage system or in other software. The blue one is the version that we developed for the aluminum magnesium system in Montreal. And if you look here at the phase diagram of aluminum magnesium, this is the magnesium rich corner. You see the HCP phase, hexagonal close pack, in equilibrium with the liquid. And there are some differences between the different liquidus and solidus. Is it a big difference? It can be a very big difference. If you're, for example, doing some semi-solid injection of a magnesium alloy for casting, the liquid-solid proportion has a big impact on the viscosity and the behavior of the melt. And as far as I know, everybody's using the type of software like FactSage to predict the solid-liquid fraction. So if you have a little difference on the liquidus, it may impact quite a lot your simulations. So having Gibbs energies for the different phases of a chemical system, how do we compute phase equilibria? So we do it by Gibbs energy minimization at constant temperature, pressure, and the different masses of the elements. So this is again the magnesium aluminum system with the hexagonal closed pack Gibbs energy curve that we predict, the FCC. We get different intermetallic solution, the liquid solution. So if you take a composition, something like 20-25% weight here of aluminum in magnesium alloy, the phase that minimizes the Gibbs energy is actually the liquid phase. But then if you get some fluctuation, local fluctuation of composition, You can then split the mass of the system between two faces and reach a minimum if you follow the tangent here between HCP and the beta phase Al12Mg17, which will be this composition there. So this is Gibbs energy minimization. Graphically, we do it with other approaches, which are mathematically more sound. But when you go then to multi-component system, for every phase, a Gibbs energy curve becomes a surface, a multi-component surface, and then we obtain plane of equilibrium chemical potential by mathematical means. So important databases that can be useful for the industry, for your research project, either academic or in the future, in FactSage. For pyrometallurgical smelting, corrosion of refractories, corrosion of alloys, we get the FT oxide database, FT salt database, and FT salt database. For solid and liquids involving oxides, sulfides, arsenides, and molten salts. Most of the classical pyrometallurgical smelting on oxide for iron making, for copper, lead, zinc, nickel metallurgy you find there, but it's also quite used in the field of glass. So a lot of glasses were developed by shot glass by different companies in the US for your smartphone involving strontium, barium, and other. FactSage was used in several of these cases. For the FT salt solution, this is more for smelting, for sulfide, arsenide. So there are many companies in Canada, North America, and even consulting firms in engineering, which are using FactSage for predicting phase equilibria, either local or global, in their work. The salt database is for corrosion, for electrolysis. Then the alloy database. So FactSage is also expanding quite a lot on the alloy side for steel, light metal alloys, and also refractory materials, silicides, carbides, nitrides, which are often used for containing materials, but also cutting tools and others. So in this case, the Steel Consortium of Professor Ino Jung at Seoul National University, our steel database is basically 38 alloying elements to iron, plus a lot of impurities there, solid liquid phases. The FT Light database, this is a consortium I'm heading at Polytechnic, but we also had projects with aluminum partners, including Rio Tinto, Alcoa, Pichney, Constellium at the time, and others. And General Motors also supported our work. Professor Medraj at Concordia University, Professor Perculevius at McGill also contributed there in experiments and in the modeling. So for aluminum magnesium alloys, titanium alloys, we get a lot of information for the phase equilibria. Who's using FactSage in the world? We have a lot of universities, typically site licenses, around 450 universities. A lot in Asia, Europe, North America, obviously. But also government labs. In government labs, either for research on energy, processes, or certification. For example, small modular nuclear reactors, they need certification, and FactSage is used for it. And we also have more than 350 licenses in research centers of different companies. So very often we have experts of FactSage, and they can sometimes move from a company to the other, and we can follow their history also in the field. So as a student, your current and future academic projects, but also your future professional projects may benefit for the use of FactSage if you're in the chemical part of the material science field. And by the way, a free FactSage Edu version is available on our website, but it's limited to 3 elements for testing. Examples of projects I did with FactSage. I'm concentrating here on projects related to the primary production of aluminum. I'm quite involved there since 1998 when I was a PhD student. The first project is a carbothermal reduction. This is a project that was started by Alcoa, Elchem, and the DOE in the US. Developments were done at ATC in Pittsburgh, Alcoa Technical Centers, but also with Professor Dick Fruin at the Carnegie Mellon University. And the plant was operated for quite some time at Kristiansand there. They developed the ARP Advanced Reactor Project. As you know now, inert anodes is a big development in Quebec, but also elsewhere. From the beginning with Alcoa project with Douglas Warrock, I was there to help them and consult, and they build on a lot of things that are now implemented in the ELYSIS approach. The development was done at ATC again, but also in Vorep and Arvida. There's things are going on in Saguenay. And you may know, but also Hydroaluminum in Porsgrunn, Norway is developing the HAL0 process. This is a process where you feed in alumina and energy, and you get out aluminum and oxygen. So it behaves like, in theory, like an inert anode, but it's using carbon and chlorine in the middle, so it's a chloride project that was announced. So these two projects are very important for CO2 mitigation, and I can tell you FactSage is also at the core of the developments that were done initially and after there. So there's also a present consortium for improving the Holyrood process with the collaboration with Rio Tinto, Alcoa, ELYSIS. Pishney was there over the time, Alcan at some time in Constellium. So the first is the carbothermal process, the ARP, again, Alcoa Elchem there. The scientific challenges we faced is basically a reactor that brings alumina and carbon to close to 2000 degrees Celsius, 2100 degrees Celsius. So we have to provide the company with simulation tools to be able to know how much carbon and aluminum you must mix at which temperature to form in the first reactor an aluminum carbide. Alumina slip. Yes, please.
If you want to go at a session at 1:30, please feel free to go, but we have the room for a bit longer. But it is, the other sessions are starting now, so I just want to make sure students know. So sorry.
Thanks, Cindy. No problem.
We can stay a bit longer, but if you need to go.
Okay, so in this process, thank you for staying. So here in this process, we form a carbide dissolved in alumina, and then you rise the temperature and you can start producing aluminum. But as you can see, the phase diagram had to be measured, it has to be modeled. These are all calculated lines here by FactSage. And the vapor pressures of the material are huge there. You get a lot of vapor to manipulate, condense, and react later on to recuperate the carbides and aluminum from it. So we modeled that for them. But as in many, many chemical processes, you develop the main reactants and the concept, but then you have to manage a lot of impurities, and these can be very detrimental to your process. And FactSage is a good tool there to understand what's going on. So in the case of the carbothermal process, you can have air leaks, so you can have nitrogen going there. What's going on then? You can have sodium in your Bayer alumina, you can have sulfur there, you can have many different elements, and how they react. So we had to do a lot of work for impurities to help them understand and guide the company toward a workable management of these impurities. So inert anodes, I was involved starting in 1998 with Alcoa in the development of the thermodynamic aspects of inert anodes. There, the solubility limits of the different elements in the electrolyte are quite critical. And again, these are calculated curves with old data. I'm not showing the critical aspects now that are, but we had to do some measurements. So in very difficult conditions, this is examples of measuring, for example, copper in fluorides and oxides. We collaborated with groups in Orléans for the measurements. And we need ultimately to have maps of the behavior of a given element with different partial pressures of oxygen, of fluorine. And the training of HQP there is very important. You acquire quite a lot of skills in doing this, and also understanding the corrosion behavior of the different materials at high temperature. And this is things that are being implemented now, and it can change industry, and they can cut millions of tons of emission of CO2 just in Quebec, but also around the world. I was visiting Rio Tinto Emera Group last week, discussing again things there. And the next project, I was also in Norway last week, is the chloride process from hydroaluminum. This is basically you take alumina, you carbochlorinate it in a low temperature reactor, and the vapors of AlCl3 are going into chloride melt. And then you make electrolysis. And the development of this project is after 2015, but we did the modeling before 2004. So they used databases that were constructed years before. And then the issues were, for us, scientific issue was before, but they were able to use the software in their planning. They are very good users at Porsgrunn Research Center since 1993 of FactSage. They hire a lot of people. I was there training tens of people there on our software. And phase equilibrium, having the correct liquidus temperature, the boiling curves, the low temperature eutectics, the vapor pressures, the speciation of the species in the different gas phase. These are things you can, with FactSage, you can test in your virtual lab, which is basically your office, before going to do a measurement, before answering questions of your boss in your future company. So I hope with these examples you get an idea of what can be done in terms of process development there. So FactSage is an essential tool, we think, for the thermodynamic aspects, phase equilibrium aspect in studying pyrometallurgical application, smelting, electrochemistry, energy, hot corrosion. But also if you're working in the field of alloys, we get one of the largest databases there. And the model and databases have been developed by academics, like I showed before, but always with collaboration with the industry to pinpoint the parts that are important, what are the needs there. And as a student, you may like to work with some computational tools like dynamically linked library. We have ChemApply for Python, which are basically tools that you can link to your own codes. And FactFlow, FactProSim are coming with the next version of FactSage 8.4, which is coming next week. And we have other tools also that permits you to take the full advantage of FactSage for helping you. So thank you very much. Would like if you have some question, but I'm also pointing here to, as part of the conference of 2011, I prepared a paper on the history of FactSage, so if you want to know more about the historical aspects of the software. So please have a look. Thank you very much.
The world is a better place for having FactSage, so you have time for questions. Yes.
Yes. Sorry, what is the? So if you want to make your own database? Okay, development of a database, in FactSage you have options to create your own. Okay, usually this is difficult things to do alone. It has to be done in collaboration with other people. So a good example there is the group in the University of Queensland, where they are doing a consortium for pyrometallurgical applications related to sulfide smelting, typically. So the group is around 20 people. And then the database, you need some training in the CalFAT technique of optimization of parameters of the different functions. Once you have the database, if you want to provide it to other groups, you can contact us in Montreal, and we can make databases that are because you get a license number that permits to use certain.
Does FactSage have any plan to develop new packages to include more components in the current databases?
Oh yeah, we are doing it all the time. A lot of extensions. There are many extensions. The thing is, we prioritize what we're asked for by different companies. Okay, that's typically how we do that. Rather, well, some of it can be patching holes that will be missing somewhere, but there are things that may look very important, but we had other priorities because of our funding or because of our different interests. But as a, let's say, a student who would like to start from scratch, already it's not that easy work to do, but there are different groups in Montreal who are doing that, by the way, and others. And then in FactSage, you can construct a database as big as you want in theory. But the commercialization aspect, because of our security system, there could be some agreement with one of the groups there, and it's possible to encode for third-party database that has been created. Okay. Just contact us. This is few groups are doing that. Usually, most groups are users. And inside a conglomerate, like say, like Rio Tinto or others, there may be many sites, so there are ways to share information within a consortia.
We are actually one of the groups here in Montreal working at ETS.
Yes.
So
with Elmira?
Yes, exactly.
Yes. Just come to see us. We'll arrange some.
Okay, perfect.
Yes, please. Yes. Yep. Yeah, sure. Okay, what FactSage does, it will calculate an equilibrium with some constraint that you put. So if you leave it free, it's a simple Gibbs energy minimization to find with all the phases available. But then you can constrain the number of phases that can participate in the equilibrium. So if you're working with a steel, for example, you don't put graphite there. In many basic iron-carbon alloys, graphite should be the primary phase, but if you remove it, cementite or other carbides can form. So that's a first simple answer. But the most important point is typically what is calculated is a local equilibrium at an interface between different materials, because otherwise you have to provide all the kinetic aspects. We would like to have other groups developing kinetic programs, okay? In thermodynamics, there are several groups doing that job. In the kinetic field, which is extremely complex, you don't have as many groups providing that. So if it's also something you're interested in, please contact us. That this is critical in material science. But for high temperature applications, usually if you take carbothermal reduction at 2000 degrees, the kinetics aspects are mostly putting materials in contact, but at lower temperature in an alloy, then there are other means there. So FactSage also has some capabilities for example, fast diffusers. If you have interstitials of carbon, nitrogen, boron in a steel, they may diffuse much faster than the nuclei of the lattice components. So these are information we try to put as much as possible in the capabilities of the software, and we succeeded for many of them. However, in terms of diffusion and the correct way of manipulating diffusion in a 3D space with all the chemistry, then there's a lot of work to do, and there's no obvious answers. It was the case 25 years ago, and it's still the case. We can answer some of the aspects there, but we cannot answer everything, and we'll have to provide more there.
Thank you very much for this exciting and interesting presentation.